Alright, so I'm going to try to break this into a couple of smaller videos this time. I just started and stopped, so we'll see how that goes. So, in order to get it, we need a hidden layer for XOR. As we saw, we also need a hidden layer to do decently at OR. Okay? So, the forward pass for our hidden layer is actually fairly simple, right? It's the same basic thing, right? We have, our hidden, so it's the same forward pass rule, that's what I'm trying to say. So we have the same, right, like output, right, for each layer is still going to be our nonlinearity of our weights times the input, right? So we're still going to have this formula, right? The input to hidden, and I should say the internal middle layer is called the hidden layer. So the input to hidden, right, is going to be, let's call it f of 1 for layer 1, w1, x1, right? And then hidden to output is going to be, right, f of 2, w2, hidden. Right? Same structure, right? Multiplying our input, which for the second layer is the state of the hidden units, times the second layer's weights, and applying the second layer's nonlinearity, right? So that's pretty straightforward. What is a little bit tricky is the backward pass. Advance. Why do you stop advancing? Yep. So again, what we actually want is the derivative of the loss with respect to a weight in the input to hidden one, right? And again, what we're going to do, I should have had the little Farnsworth picture down here. Because we are going to, once again, deploy the multivariable chain rule, and we wind up with this rather intimidating thing. Okay? But there's a trick, fortunately. Before we had this, and what we notice is part of this repeats. This matches up with this, right? So part of the update for our output to hidden, part of the update for the hidden to output units, output units shows up, basically, or something like it shows up in the update to the input to hidden units, right? And it gets transformed according to the output weights. Then, if you kind of cross this out, you notice that it also kind of repeats, right? Because what you're looking at is some junk that is a function of the previous layer's update. Let's see if this will work. Some junk that is a function of the previous layer's update times gradient of our activation multiplied by the input to this layer, right? So the thing that we wind up with is stuff times gradient times input, okay? Loosely speaking, without wanting to get too technical, we actually can separate that out, all right? What it turns out we can do, and yep, that was all useless, is we get rules like this. Stop it. So between those two things, this is the part that I underlined in purple, right? This is the junk. That's the wrong color. Turn purple. I want you to turn purple. There we go. This, right, is a rule for taking, so this is a rule for taking our error and producing an error for the previous layer, right? This is the rule that is derived from the bit I underscored in purple before. This is how we take the layer for the upper layer and transform it to get the error for the previous layer. Did I? All right, I'm sorry. Third time is the charm. This is the rule for taking the error for the previous layer and transforming it using the weights for this layer and the gradient of its activation function to get the backpropagation error, the error that we're going to use for the lower layer. Okay? And the lower layer is going to use the same weight update rule, because remember, this part was the same, right? So what we're basically doing is we're taking the error, we're computing the weight update for the layer we're on, and then we're using this rule to transform the error to get a backpropagation error, and then we're applying the same weight update, right, but with the backprop error rather than the top error. And we can keep doing this, right? It turns out that loosely, again, sort of loosely speaking, the pattern that we're exploiting keeps holding, right? If you keep doing the chain rule, if you add a lot of layers and then do the chain rule a bunch, you find out that this relationship keeps repeating, right? 4 layers, 5 layers, 6 layers. It keeps looking like this, right? You keep being able to apply, to use this as your weight update, right, which is the same rule that we used before, and you keep being able to pass the error backwards with this. Okay? So here is the complete forward pass of our 2-layer network. All right? Excuse me. We notice, again, that up here, the forward pass from layer 1 to layer 2 is the same as the pass from layer 2 to the output, right? We compute our pre-activation by multiplying the weights by the input. We get the output of the first layer by applying the tan H nonlinearity. Again, tan H is kind of arbitrarily chosen. There are other nonlinearities we could use. I just like tan H. And then, to get the next layer output, we get the pre-activation for layer 2 by multiplying the layer 2 weights by the input to layer 2, and then applying layer 2's nonlinearity, which is tan H again, but it could be different, right? And a note is that these don't have to be the same. We could use different nonlinearities. We'd always have to apply the right derivative, right? Get the derivative of the right function, but we easily can give each layer its own activation, right? Its own activation function. And then in the backwards pass, at the top layer, our error is our error is just our error, right? It's d minus m, and then we have the same weight update rule we had before. And then to get our backprop error, we use that backprop error rule, right? And then we just apply to update the bottom layer, we apply the same update, right? So we're using the same update rule, we're just using the backpropagated error, okay? Notice that we actually apply those weight updates after we compute them, right? So we compute the deltas, right, the updates for the first weight layer, for the top weight layer. Then we compute the deltas for the bottom weight layer, and then after we've computed and stored them, we apply both of them at the same time. The reason that we wait to do that is because, right, the output weight, the weights of the output layer are a term in computing this backprop, and if we went ahead and applied the updates here, we'd make this math here wrong, right? This would have changed, and it would make it would introduce errors. It would make our backprop error slightly wrong, right? So that's why we want to compute all of the updates and then apply them after we've computed all of them. So, I had y'all do a bunch of matrix math exercises. Not always, but very often, working with neural networks, we can look at the dimensions of our output. We can look at the dimensions of the dimensions of the results of our math to see if we're doing it right. Not always, but a lot of the time, right? An early signal that you've screwed something up is if you compute the output dimensions for the thing you're trying to do and it doesn't add up to the dimensions that you need, right? So let's take a minute to sort of do that right here. What is the dimension of this error, right? So if you remember what our architecture was before, it was 2 to 3 and then 3 to 1, right? Same number of inputs, same number of outputs. The first weight layer, right, what is it? Well, it is 2 to 3, 2 inputs to 3 outputs. Therefore, whoops, that was weird. It is a 2 by 3 matrix, right? The second layer is 3 input to 1 output. Yeah. Therefore, it is a 1 by 3 matrix, right? So, this is 2, this is 1, right? I'm calling this layer 1 and this layer 2. So what dimensions will D minus M have? So take a minute to think about it, right? Pause the video. D minus M is going to be, right, a 1 by 1 matrix. What is D matprod the input to 2 going to be? Well, this, right, this thing is the output of 1 and the input to 2. So it's a 3 element. Oh, the way I've written this, I think it should be a 3 element column vector, right? What is a 1 element by a 3 element column vector going to get me? So this is 1 by 1. This is 3 by 1. Oh, okay. All right. Sorry. So that's going to get me nothing because I'm stupid because it's transpose, right? So 1 by 1 by 3 by 1 would not work at all. That is forbidden. But it's transpose, right? So it's a 1 by 1 matrix on this side. Here, you know what I'm going to do? I'm going to get a different color. So it's a 1 by 1 matrix on this side. And then it's a multiplying it by, right, a 3 by 1 matrix that is the input, but it's the transpose. So we turn it on its side and it becomes a 1 by 3 matrix, right? Because it's the transpose. So 1 by 1 times 1 by 3 is 1 by 3, right? That is the dimensions that our weight matrix is going to have, right? 1 by 3 is the dimensions of our weight matrix, so our math makes sense. Now, what about the next layer, right? Excuse me. So, when we want to pass our error backwards, W2 is this 1 by 3 matrix, but we're transposing it, so it becomes a 3 by 1 matrix, right? Transpose of this 1 by 3 row is a 3 by 1 column. And we are multiplying that by our previous error, right? What was our previous error? It ended up being, oopsie. Our previous error was, I'm sorry, I'm juggling keys. Green still? Yes, still green. Our previous error, right, was that 1 by 1 matrix. So again, now we're going to get a 3 by 1 times a 1 by 1, and that's going to produce a 3 by 1 matrix, right? And that's what we're going to assign to backprop error. So that intuitively makes sense, right? We have one error term for each weight in this layer, right? So backprop error for layer 1 is a 3 by 1 matrix, right? Oh boy. And my digital screen whiteboard is now getting a little bit busy, right? So let's erase all of that, and let's verify that that's going to produce the dimensions that we want, right? So remember that, I gotta redraw some of this. Right? So remember that our W1, our first weight matrix, is botched because I'm dumb. Okay. Right? So let's try this one more time. Right? Our layer 1 is 2 input, 3 output. So it, and I think I might have screwed this up a minute ago. Nobody rewind the lecture to see. Nobody look. Right? It's 2 output. No, it's 3 output. Ah! Okay, right, it's 3 output, 2 input, so it is 3 by 2, right? This is easy to screw up. I screwed it up a while ago and left it there, looked at it over and over again, didn't do anything. It's 3 by 2 because it's 2 input, 3 output. All right, and our BP error is, why did I draw that line? Our BP error is 3 by 1. Right? We just found out that our BP error is 3 by 1. Right? So let's make sure let's make sure that the dimensions add up correctly. All right? Oh Lord, I needed another cup of coffee before doing this. I apologize. So our BP error is a 3 by 1. Our W1 is a 3 by 2. So what does our update rule get us? Well, we know what dimension this is, right? That's this 3 by 1 thing, right? So what is the dimension of that? Well, the input is a 2 by 1, right? The original input to the bottom layer, to layer 1, was a 2 by 1 matrix, right? So the error, right? The error term, and the error term times the input term is going to be a 3 by 1, use the colors consistently, it's going to be a 3 by 1, right? Times a 2 by 1, right? Oh, I did the same thing again, but it's transposed. So our 2 by 1, because it is transposed, right, dot t, becomes a 1 by 2. And a 3 by 1 times a 1 by 2, because our 2 by 1 is transposed, produces a 3 by 2, right? That is our weight updates. And yes, that is, the thing that we wanted, right? So I apologize if that's difficult to follow because I tripped over myself a whole bunch, but we do know, hopefully, right, that all of our matrix dimensions line up. So another point that is worth making real quickly, that I kind of skipped over, is I assumed it was obvious that error and this thing, the derivative of the input, has the same size, right? They have to because they're being pointwise multiplied together, right? But I didn't stop to make sure of that. So let's look at least at this layer, right? If we know that error is this 3 by 1, right? What is the derivative of the activation function of our pre-input? Well, that's the same size as the pre-input, right? This y thing. What was the pre-input? Well, it is our W1, our first weight layer, times X1, our input. What size is that? Well, W1 is a 3 by 2, that's the weight matrix. Input is a 2 by 1, that is the input. Going slowly to make sure I don't say something dumb, right? Did I say something dumb? No, I didn't. Good. Okay, and that is going to be 3 by 1, right? So m times an m by n times an n by o is an m by o, right? If you don't know those are the letters M, N, and O, it sounds like a strange chant, right? But that's this, right? A 3 by 2 times a 2 by 1 is a 3 by 1, right? So this thing right here, this thing right here, right? D tan H of Y1 is a 3 by 1 matrix. And this thing over here, the backprop error, is a 3 by 1 matrix. And so yes, we can compute the pointwise product of those. So I'm sorry if that's a little bit stumbly and we're kind of going to have to maybe think through that very slowly and cross some stuff out, but we do see good, our matrix dimensions for all of our matrix products all line up. We're getting the sizes of matrix that we expect. That is a good sign, right? That's a nice little error check. And this is why I made you guys do a whole bunch of matrix math, right? Why I made you what is the dimensionality of this matrix product? Because it sort of helps you look at this and go, now did I screw something up, right? It's useful. So, all of that being said, yep, we know that. If we train this on the OR rule, we see much, much better behavior, right? It is possible for this network to approach very, very close the output that we want. Notice, actually, that this case, the 0, 1 case, is still very, very slightly less than the target, and this case is very, very, very slightly more. I'm going to say something that might be stupid. I do not think that mathematically it has to be. I think that's just an artifact of the fact that floating point math is imperfect, although I could be wrong. In either case, note that these things have come within a really, really tiny delta of the target we wanted them to have, right? So adding our second layer has dramatically helped, right? There's our loss for the OR rule. And again, notice this time that once again it really rapidly converges, and then not much happens, right? So I really didn't need to train it for as long as I trained it. So what about the OR rule? Well, excuse me. We see that it does a superb job with the OR rule, right? We get pretty much exactly the target we wanted, and then we get, 8.8 times 10 to the negative 16, right? So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Very, very small, arbitrarily close to 0, right? As close to 0 as we could want it to be, right? So with 2 layers, our network is able to easily learn this rule, right? So a fair question to ask is, at this point, we know the input needs to be 2 units, right? Because if we look at one of these rules, right, we know that we have 2 inputs. We know that the output needs to be 1 unit because we have 1 output. Why did I pick 3 for the hidden layer, right? Why didn't I use 4? Why didn't I use 1? Why didn't I use 2? Well, an unsatisfying answer for now is no damn reason, right? I kind of figured I needed to have at least 2 layers, because I need to sort of have 1 unit that can be active in this regime, and 1 unit that can be active for this different regime. That's basically it. I didn't try it with 2. Would it work with 2? It might, right? I didn't try it with 4. Would it work with 4? Almost certainly, since it works with 3. It probably wouldn't work any better, right? There is sort of a little bit of a black art to designing your networks, right? There's sort of kind of a couple of general rules you learn, and then intuition plays a role. But I do not have a mathematically robust answer for why I picked 2 to 3 to 1. And there is, so I forgot that slide was next, but there is what our loss does for XOR. Notice once again that it very rapidly, with a little bit of confusion, converges and then stays basically at 0, right? This is the loss, right? So the loss, the error, converges incredibly rapidly and then just stays 0. All right.